Okay, guys. Sorry I had to be out again today, but today is Wednesday. It's the 14th. We're going to start working with exponential functions. Here's a graph that I drew for you. Y equals 3 to the x. I went ahead and made your table there. If I plug in a -2 there, I get 1/9. If I plug in a -1, I get 1/3, and so on. Remember, any number to the 0 is 1. And then 3 to the 1 is 3. 3 squared is 9, and there's your graph. Remember, you have a horizontal asymptote at y equals 0. And here's just a bunch of characteristics about this graph. You can see the domain of a graph is always going to be all real numbers. The range goes from 0 to positive infinity. The y-intercept is at 0, 1. This graph is increasing. It's always continuous. It's concave up. It never equals 0 because of that horizontal asymptote. And the limit of f of x, the limit of the graph, remember this is in behavior, so the limit of the graph as x approaches negative infinity, so as this graph goes to the left to negative infinity, it's getting closer and closer to 0, so that's your limit. The limit of f of x as x approaches negative infinity is 0. Okay? So let me show you some other examples of some transformations. Remember, if I add 4 up there in the exponent, if I subtract 4, that moves it right 4. So that critical point that was at 1, 0, 1, is now at 4, 1. The asymptote doesn't change. The graph stays the same. It just moves right 4. Here's an example. If I switch that around and make it look like negative x, put the negative, the variable out front, it's pretty obvious to see the reflection, but be careful because we know that, this looks like it moves left 5, but we need to make sure we factor out that negative, which we've talked quite a bit about. So factor out that negative and you can see that this graph actually moves right 5. So we've got an a out here, which is -1. This is not your a, this is actually the base. It's part of the exponential. So you would have to have another coefficient out front. So let's say that I had an a of 3. It would look like this. That would be an a of 3. Okay, so this a is -1. The b is also -1. The c is 5. If this is x minus c, the c is 5. And the d is a +1. So your graph, if this is your parent, we would flip it over the x-axis first. So now we're down here. Then we would flip it over the y-axis. So now it looks like this. We would move it right 5, so that critical point that's at -1 there moves right 5. And then the d is 1, so it moves up 1. So there's your graph. Because it moved up 1, the near horizontal asymptote is now at y equals 1. Here's your domain. It's always going to be all real numbers. Your range comes up from negative infinity all the way up to 1, and it's non-inclusive at the 1. Great. So now let's look at some solving. If we have 9 equals 3 to the x plus 1, I want to use what we call the 1-to-1 property. And what that says is, if I can get the same base, meaning if I can rewrite 9 with the base of 3, and everybody knows that that's 3 squared, if I can get the same base, the 1-to-1 property says that this exponent, if these are equal, then this exponent has to equal that exponent. So we can drop the the base there and just set the exponents equal to each other. So we get 2 is equal to x plus 1, and then you can solve for x and get your answer. Okay? Let me show you one more like that. Let's take 1/2 to the x, set that equal to 8. Then I can say that 2 to the negative x is equal to 2 cubed. I've got the same base, so I can set my exponents equal to each other and get my final answer. Ooh, I'm sorry. Let me say that again. Just to get the same base, I know that that one's 2 cubed, so the 1/2, I can rewrite it as 2 to the negative x. And once I get my same base, then I can set my exponents equal to each other and solve. Okay, here's another one. If I've got 25 to the x plus 2 equals 125 squared, then a good base to use for both of those would be 5. So this could be 5 squared to the x plus 2. And then this could be 5 cubed squared. And then we can work that out. So we're looking at 5 to the 2x plus 4 equals 5 to the 6. Got a same base there, so now we can set our exponents equal to each other. And then we can solve from there. Okay, one last problem. Mr. Coffee, if you need to pause this at any time and let them catch up, then feel free. One last problem as far as the one-to-one property goes. If you take 9 squared, and that equals 27 to 3x plus 1, then I can change that to 3 squared, and then 3 cubed to the 3x plus 1. And then we can work it out from there. So 3 to the 4th is equal to 3 to the 9x plus 3. So then we can drop the bases and say that 4 equals 9x plus 3. Subtract the 3 and divide the 9. So x would equal 1/9. Very simple way to do it. Actually, I'm going to show you one more like that, but let's do it with the rational number e. Let's say that e to the x squared minus 3 is equal to e to the 2x. Since I have the same base, I can drop it and say that x squared minus 3 is equal to 2x. Because we've got a quadratic, we want to set that equal to 0. So subtract the 2x from both sides. Then we're going to factor. So x would equal 3 and negative 1. Okay, so that will conclude part 1, and then I'm going to come right back to you with part 2.